Hi, I'm Ashley.
And I'm Jarrett, and this is halogenation, nitration, Friedel-Crafts alkylation, and acylation of a benzene ring. Due to the aromaticity present in benzene, it's going to be very difficult to actually get benzene to react. As you'll see throughout this section, preparation of specific reagents is required to break the aromaticity of benzene and add substituents. Preparation of reagents begins with this mechanism at the bottom. An electron pair from the bromine attacks the iron, forming a negatively charged iron and a positively charged bromine. Obviously, a positively charged halogen is not stable, so an electron pair will move from the bond to the bromine, forming iron with a negative charge bonded to 4 bromines and a positively charged bromine. This will be strong enough to break the aromaticity of the benzene ring. The positively charged bromine will then participate in the reaction, with an electron pair from one of the pi bonds in the benzene attacking the bromine. This breaks the aromaticity of benzene and puts a positive charge down on this carbon. We can then use our negatively charged FeBr4 as a base. It'll take a hydrogen and push an electron pair back onto the carbon, reforming the pi bond, and thus ending our halogenation reaction.
Next, we're going to look at the nitration of a benzene ring. To add a nitro group to a benzene ring, we have to react the ring with HNO3 and H2SO4. However, initially, HNO3 is not a strong enough electrophile to pull electrons away from the stable benzene ring. First, it has to undergo a reaction with H2SO4, which is shown below. In the reaction, the lone pair on the oxygen here pulls a hydrogen away from the oxygen on the H2SO4 here. This leaves this oxygen with a positive charge and this oxygen with a negative charge. This gives us HNO2 plus and HSO4 minus, which we then use in the nitration reaction above. In the reaction above, the HNO2 plus is now a strong enough electrophile to pull the electrons from the benzene ring out of this pi bond, forming a bond with the HNO2 plus. Then the HSO4 minus can act as a base, pulling the hydrogen away from this carbon and restoring the aromaticity of the benzene ring. This gives us a nitro group on our benzene ring. Really quick, note that there is a split charge on the HNO3 as well as on the HNO2+. This is because nitrogen does not have a low-lying d orbital and cannot expand its octet. In other words, nitrogen can only have 4 bonds.
Friedel-Crafts alkylation is similar to halogenation in that in one step in the formation of the reagents there's a positively charged halogen. If we look at the reagents down here, we see that we have AlCl3 reacting with an alkyl chloride. As usual, the electrons from the chlorine will come and attack the aluminum, forming this complex over here. Unlike other reactions, though, this chlorine will not break off, and we will not be forming a positively charged carbocation. This is because of the structure of a primary carbocation. Clearly it's very unstable, and so it likely would not last very long at all. So we get our big group down here, and it moves up and gets attacked by the pi bond on the benzene ring, pushing an electron pair back onto chlorine. Again, this breaks the aromaticity, and we can use the newly formed AlCl4- to take a proton and therefore restore the pi bond and the aromaticity of the benzene ring.
Lastly, we're going to take a look at Friedel-Crafts acylation. Acylation is just the addition of a ketone to the benzene ring. In order to add a ketone to our benzene ring, we're going to react it with an acid chloride and AlCO3. Like in all of our previous examples, the acid chloride is not initially a strong enough electrophile to pull electrons away from the benzene ring. It first has to undergo a reaction with the AlCO3, where the chlorine attacks the Al, which does not have a full octet, giving an AlCl4- in this structure here. We now have a strong enough electrophile to pull electrons away from the benzene ring. Electrons come from this pi bond and attack the plus charge on this carbon, forming a bond between the two carbons. Next, the AlCl4 comes in as the base, and the negative charge deprotonates this carbon, restoring the aromaticity of the benzene ring, giving us our final product.